Good morning, everyone. Today we continue our discussion of time series. We're going to review some of the concepts that we learned last time. There's nothing wrong with reviewing because I think reviews of lessons will allow us to have better comprehension and better grasp of the uh, concept and the techniques and the methodologies. So we're again going to load uh, forecast, T-series, okay, quant mode, technical trading rules, KFAS, and then ggplot. Okay, so I'll delete first. Okay, I'll delete all my objects there so that I'll start from scratch. Okay. So last time we started discussing about time series and its role. Okay. In finance, time series analysis play a very important role. And we said that there are components to time series data. You have the trend, the seasonality, okay, which are easier to model compared to the cyclicality. Okay, a cycle usually is over the long term, and it's really difficult to predict that. Okay, then you have the noise, the irregular component, that which cannot be considered as part of trend, part of seasonality. Okay, they are considered as noise. And then we used air passengers last time. Okay, so I have to run this because I already deleted it. Control Enter. If you still have your object air passengers, then you don't need to run this. So we saw that this airline passengers data has trend and seasonality. Okay. Fortunately, it's taking some time. Okay, and then we created an object AP to represent air passengers, primarily because air passengers is quite long to run. Okay, so I'll just run this, Control Enter, and see the plot. So you can see here that this data displays trend. Okay, and seasonality also. You can see the peaks and troughs, peaks and troughs, peaks and troughs. Okay, so that's seasonality. Now we said that in time series analysis, there are methods that require that your time series be stationary. So we said that stationary has two dimensions, stationary in mean and stationary in variance. When we say stationary in mean, it it, it means that the average, the mean is constant. Okay, so your data across time, this is your, say this is your data. Okay, this is, oops, except for some of the spikes here. This data displays stationary in mean. Why? Because if you if you analyze several periods of the data, the average still here. Okay, the average does not change across the different time periods. So this we say is stationary in mean, and this also is stationary in variance. Okay, you notice that okay, the upper and the lower limit do not increase over time. If it was behaving this way, okay, you can see that there is an increase, okay, in the variability of your data. As you increase your time period, you notice that the variation increases. So this we say is an example of a time series that's although it's stationary in mean, okay, because there is really no trend. It's not going up nor going down. However, it's not stationary in variance. Okay, then last time we said that there are statistical tests that we can use to determine if indeed statistically the data is stationary. Okay, and we started with the ADF test. So the ADF test, okay, has its own, let's say, weakness. Okay, the null hypothesis is that the data is not stationary. The ADF test might have difficulty with identifying the trend. Okay, so if we run this, the augmented Dickey-Fuller test returns. It's running so slowly. Okay, augmented Dickey-Fuller test, ADF test. The null hypothesis is that it has a unit root. Okay, now having a unit root is quite different from determining if there's a trend. Okay, now here the Dickey-Fuller statistics is negative 7.3. The p-value is 0.01. So which means that we are rejecting the null hypothesis that the data is not stationary. Okay, airline passengers, as we saw, is not stationary. So based on the ADF test, okay, we're not. It tells us that the data is stationary. Okay, that it has no unit root. So you can see here, especially in time series that have a trend, the ADF test might not work very well. So in comes the KPSS test. So this is where we had I had some problems. I checked the syntax. Okay, when you say that it has trend stationarity, it means that it has a trend, but the data is stationary with respect to the trend. Okay, so that's what the KPSS test. Okay, so I apologize for getting confused last time. Okay, if you take a look at our data, so here the KPSS test is actually correct. So it's saying the assumption is that it has a trend. Okay, all right. So in that regard, uh, the KPSS is correct in saying that it has a trend. Okay, because the assumption here, the null hypothesis is that it is trend stationary. What do you mean by trend stationary? Okay, it's telling us that although the data has a trend, yet it is stationary in its trend. Okay, in other words, it has a trend, but it still displays stationarity in that trend. Okay, so that's what this is saying. Okay, so strictly speaking, if it has a trend, then we can say that it is not stationary. Okay, because it has a trend. Okay, so that's what the KPSS test is proving. Okay, so I apologize last time. Uh, I got confused here. I checked the documentation of the KPSS test, and then it's testing. Okay, what it is testing is that when you say trend stationary, it has a trend. Okay, however, in that trend, it is stationary. Okay, so what we got here, okay, so the null is equal to it has a trend. Okay, so if we run this, please run. Okay, it's taking from my computer to, all right, and then the p-value is 0.1. Therefore, what's our conclusion here? We fail to reject the null hypothesis that indeed it has a trend, okay, but it is stationary in its trend. Okay, so that's something unique about the KPSS test. Okay, in fact, if we KPSS that test, let's check the syntax. Okay, so I hope you got that. The null hypothesis is that it's saying that there is a trend, okay, but it is stationary in that trend. So I'm waiting for the help function here. Okay. very slow. My computer is very slow. Okay, so we can actually test this. It is at level. Okay, that I didn't test last time. So if we, okay, let's copy this. Control C, Control V. And then instead of null is equal to trend, I'm going to put here level. Okay, and what will be the result here? Okay, now you can see that the p-value is different. Because this one, the null is equal to level, is saying that there is no trend. Okay, so you can see the difference with the KPSS test. There can be an assumption that there's a trend, and there's also an assumption that it is at level, no trend. So when we indicate that the null is equal to level, we're saying that there is no trend. Okay, and we reject that. P-value is equal to 0.1. We reject the null hypothesis that there is no trend. It's at level. Okay, your time series is at level, which means that it's not going up, neither is it going down. So the KPSS is correct after all. Okay, because what we used last time is that null is equal to trend, which assumes that there is a trend. However, your data is stationary in that trend. Okay, for this one, null is equal to level. It's telling us that your data does not have a trend. Okay, that it does not have a trend, then it's stationary in that there's no trend. So that one we reject. But this one, there's a trend, but it is stationary in that trend. We fail to reject. Right? Either case, we were able to show that that technically there is it's not stationary because there's a trend here. Okay, although it's constant in that trend, which means that the variance is constant. Okay, let me pause for a while. I hope that I have cleared this because I'm sorry I might have caused you confusion about the KPSS test. And the KPSS test still remains to be a better and more powerful statistical test compared to the ADF test. Okay, is that clear, class? Please, may I have your confirmation about KPSS test, where the null is equal to level and the null is equal to trend. Hello? Feedback, please, class. Okay, thank you. Thank you. All right. Okay. So now we said that, especially when we get to ARIMA, which will be on Monday, okay, when your data is not stationary, just like air passengers, what we need is to transform the data. How do you address the trend? The trend is addressed by getting the what class? Getting the So how do we address the trend? Okay, let me plot this again. Okay. All right. Taking long again. Okay, here. We know that our airline passengers, AP passengers, has a trend. Okay, so what's one of the most, say, popular transformation, because we need to transform our data in order to remove the trend. And okay, so let's create an object called DAP, and that DAP is the difference of your AP. And let's plot DAP. Okay, differencing class, okay, take note, differencing removes the trend. Okay, although it might not remove the non-constancy invariance. Unlike, so I'll create another one, LAP. Okay, LAP is log of AP. And then let me plot this, plot log plot LAP. Okay, so here I'm getting the log of AP, and then I'll plot it, control enter. You can see that getting the log, okay, might cure the non-constancy invariance, okay, but it will not cure the trend. So when you're dealing with the time series that has that is not stationary, which means it has the mean is not constant, the variance is not constant, okay, and therefore the covariance is also not constant, then what we do is, in order to address both, if there's both, okay, what you have to do first is it getting the log and then getting the difference, or getting the difference and then getting the log? It's always getting the log first, so you get the log, so we get the log of AP and then get the difference, okay? So that this is how we transform our data. So get the log first of your AP, okay, and then get the difference. There. So it's difference log AP, okay? And then if we plot this, let's plot the difference log AP. Okay, you can now see that we were able to address the non-constant mean and non-constant variance. We cannot do it reverse, log the AP, okay, AP. So here we're getting the difference first, difference of AP, difference of AP, and then get the log. Now this will not work because the difference of AP will generate negative values. Okay, when you subtract one value from another, there's a big chance that there will be negative values. And you cannot get the log of negative values here. So warning, and not a number produced. You cannot get the log of a negative number. Okay, so I hope that's clear, class. That's a quick review of what we have discussed, class. Okay, so in this case, we got okay, so we created this object, log air, which is the log of AP. So we get the difference of log air and called it diff log air. So let me run this, control enter. Okay, and then actually we plotted this. Okay, plot diff underscore log air passengers. Okay, you can see now that visually it seems to be stationary in mean and stationary in variance. So we can test this kpss.test, okay, and use diff underscore log air, and then let's try null is equal to, okay, null is equal to level, capital L. So here we're saying that there's no trend. Okay, we're saying that there is no trend. Control enter. Okay, take a look at this, class. No trend. See now the p-value. The p-value tells us that we failed to reject the null hypothesis that there is no trend. Null is equal to level. Okay, same thing will result if you use null is equal to trend. All right. So for the ADF test, also the same. Okay. Now, okay, I don't think we discussed this last time, but take a look at this, class. Here, we're creating another object. It's diff log air seasonal. And you notice here that diff log air is the differenced class. And then we do another differencing, and then the differencing is on the seasonal, okay, every 12 on the seasonal component. Here we just difference on the daily data. Okay, here we're differencing by the season. So it's December to December, November to November, etc. So let's run this. Okay, so we create this now, diff log, and let's plot this. Let's see how this plot looks like. Okay, so you notice that unlike this one class, diff log air, let's plot this. This one, although not that apparent, but it seems to have some seasonality. You can see here some patterns. Okay, up, down, up, down, up, down. Okay, there seems to be some patterns here, but compared to this one, where we remove the seasonality, okay, you notice now that there seems to be no pattern anymore. Okay, all right, so this is now differencing the season, and we're using lag 12 because this is monthly data. Okay, and same thing, if we get the KPSS test, it will return, and if we do this, and then let's identify that null is equal to level. Okay. Then we also get a p-value that, okay, there, a p-value that's greater than 0.05. So the conclusion is that we fail to reject the null hypothesis that this has no trend. Okay, but because indeed there's no more trend, and the seasonality seems to have been removed. Okay, then here, class, we learned about the decomposing your data. So our data is AP, and then we're creating this object decompose. Maybe I should have used decompose AP. Let's change this. Since we're using AP and not air, AP, and then AP. Okay, all right. So let's first decompose. When you say decompose, it will split your data into the trend, the seasonality. Okay, let's plot this. Here, the trend, this is your original data. This is your seasonality. Okay, this is your trend, and this is your irregular component. Okay. Then you can actually print the trend. Okay. So it's the decomposed object, decomposed AP, and then the time series. If we run this and print this trend, let's call this just TR, okay? Alt minus trend adjusted. Okay, maybe you would like to have it printed. Okay, so I'm printing both the trend adjusted and plotting it. See, all right. So here is your data. Here is our data. Okay, so this now removes the seasonality component. It will only give us the trend, and I plotted it. Okay, so you can see here there's no seasonality here, only the trend component, which is this one, class. This one. Oh, sorry. Where's the here? No, not that one. Here, the decomposed. Okay, class. This one. This one, which we were able to plot here. Okay. All right. So there are different ways in order to model your time series. For your case, you'll be working with a different tools, SMA, EMA, Okay, exponential smoothing. So last time we started with smoothing. Smoothing is one of the easiest, and the formula, okay, I will not discuss this so much anymore. It's just getting the average. So you sum and then get the simple average. This is just a simple average, where K is your lag. So if you say K is equal to 5, then it will add the 5 previous values, okay, and then divide by 5. So that will be your first prediction. Okay, and we learned last time that the bigger the lag, the more smooth your data is. Okay, so this one has, okay, we're using SMA. This is simple moving average. We are getting the simple moving average of AP. We're plotting it, okay, and then we're also creating the lines for SMA4. Okay, so if I run this, plotting it, okay, this is your SMA4, 4 months since our data is 4. If you compare that with SMA36, okay, let me plot the whole. So we have 4 plots here. This is your SMA36, right? This is your SMA4, 4-month moving average. This is your SMA12, and this is your SMA24. So you notice that the the bigger the lag, the more smooth your predicted values are. Okay, so we discussed this last time. May I have a confirmation, class, if this is clear to you? This is important because this will be part of your case. You have to know how to get the smooth, the simple moving average, etc. And then you're going to compare among the models, okay, which is the better performing one. Of course, I suspect that SMA will always have a high Ramsey. Okay. Here, if it was 2 class, if it was just 2 months, we said last time that this will generate a data, a prediction that almost mimics your data there. Okay, maybe let's change the gray into let's make it, let's say, about blue. Okay, so the gray one can't be seen really. All right, there. The original is your blue, plus AP is colored blue. SMA2 is your red. Okay, you can see how practically your time series model SMA2 is mimicking your original data, AP. All right, and last time here we created a table, 2, 12, maybe we can include here 4, okay, maybe a 6, 2, 4, 6, 12, 24, 36, and we're creating the plot, okay, plot for AP, and then for lag values, these are your lag values. So what will happen is that it will loop here, okay, 2, 4, 6, 12, 24, 36. So the smooth data, okay, it will filter it out using the original AP, and then it will repeat the process of 1 over lag, and then lag. Okay, let's see how this runs. Okay. Did I change the colors? Hindi ko na change yung colors. Okay. Although, there should be different colors because I use these colors, open and close parentheses. So you can see here, okay, the one that really mimics your data should be this one, should be your SMA2, and then followed by the yellow one should be your SMA4, the red one should be your SMA6, okay, this one, the green one, should be your SMA8, okay. it should be your SMA 24, and the black one should be your SMA 36. Okay, so it's easy to determine which is which. This one, of course, the first one here should be your SMA 2 because you only have 2 months and then you already have your prediction. Okay, so different SMAs here, and it just reinforces what we have said a while ago that the smaller the lag, the more close it is to the original data. Okay. All right. Now it's important to, so let's add here 2, 4, 6. Okay. So which model is better? Okay, based on root mean square error, class. Do you recall what's root mean square error? Root mean square error is, okay, it's your actual value minus your predicted value, right? Squared. So you have to square your errors and then get the average of all your squared errors and then get the square root. Okay? So it's the square root of the mean, okay? And then the actual minus your predicted value squared. So that's the formula there. Okay, and then we will print the results for your Ramsey for lags 2, 4, 6, 12, 24, 36. And we will guess, we could guess really with certain accuracy that the SMA2 will be the one that has the least amount of Ramsey error. Yeah, Ramsey. Okay. Come on, run. Okay. There. All right. So for lag 2, it's 31. For lag 36, it's 137. You can see here that the root mean square error is highest when your lag is highest. Okay. Now, I modified the model so that we don't have those error terms by trimming it. Okay. So this one will trim the data. Okay. It's quite similar to the other one, only I just added a trim function here. Okay, here, actual trimmed. Okay, I trimmed those values that are, because if you recall, class, SMA 36 will have less data than SMA 2. Okay, so that's why the message here was the values are not the same. Okay, so if we trim those that are if we make the length of the values the same, then and run this. Okay, please work. Okay, you can now see that the values change, class. Why did the value change? Because there were some values that we cut off. So we had to base it on the number of observations for SMA 36. Okay, so how many observations does SMA, okay, SMA 36 have? SMA 36 has, okay, so you have NAs there, right? You have NAs there because for the first 35 observations, you have NAs. All right. For SMA2, you have only one NA. So definitely SMA2 will have more observations. Okay. So in order to make them equal, okay, we trim those that are not present in the other data. All right. Then quickly now, I hope the review class of SMA helped you. Is it clear, class? The simple moving average. Take note, class, that that's included in your case. But it's actually easy, class, because the function is just SMA, class. How do you get the SMA? It's just SMA. here, SMA, simple moving average. Okay, then again, class, may I have your feedback if we're clear about SMA? I want to reach exponential times smoothing. Class, feedback, please. Hello. Hello, class. Are we clear so far? Okay, thank you. I hope you can respond quicker, class. All right, thank you. Okay, so let's now go to another review class is your uh, EMA. Okay, the next one is your exponential moving average. We'll go to this quickly. Okay, did I discuss this class? This one, SMA in stock trading. Did I discuss this? I think I did, class, right? How is SMA used? Practical application of SMA in finance, in stock trading. I discussed that, right, class? Mm. Yes or no, please? Hello? I don't know if it's my computer or medyo your response time is just quite slow. Okay, only one response? Okay. All right, so we discussed this. So anyway, class, uh, you have the notes here already. SMA 50 and SMA 200. Okay, so this is used for stock trading as as a signal, as an indicator. Okay, and the simple rule is that, okay, what's our rule, class? Okay, when your 50-day moving average goes above the 200-day average, so that's considered as a buy signal, while if your 50-day SMA goes below your 200-day, then it's a sell signal. Okay, so these are used as indicators. Okay, so we did that last time. All right, now let's go to EMA, exponential moving average. It's practically the same as your SMA, okay? Only that you the weight that you give to your previous data is not equal. In SMA, simple moving average, it's just equally weighted, 1 over K. So if you have, let's say, 5, if you're doing SMA 4, okay, then that means you have the past 4 observations, you add everything, and then you divide by 4. It's simple average. On the other hand, for for exponential moving average, okay, what do we do? The formula is different. Okay, you also average it, but it's a weighted average. Okay, it's a weighted average. So this one we ran last time. Again, we're using air passengers, AP. Okay, and then we're converting AP to a numeric. Okay, then we have this function here. We make use of AP and N. Okay, this is the formula for your EMA. Okay, and then we create several EMAs. Okay, so here, so this should be 12 class. Initially we had 12, but you can change this because here N will be dependent on this one. Okay, so let me start with EMA 12. All right. So same principle as same principle as SMA. Okay. So the lower the lag period is, so for example, if I use 2 here, okay, 2. So 2 will be applied here. Okay. I can run this. Then you see now that it, just like SMA, EMA behaves in a similar manner. So the lower the lag, the more it follows the the more it follows the original data. If I have here 36, okay, so that's 36 months. And you can see that it's actually quite smooth. Okay, all right. So here, let's EMA function came from this one, right? We created this. This is our code EMA function where you have to put AP and N. So we're following that AP, the object, and your N. So this is a comparison between log 6, log 12, and log 24. And then we're plotting it here. So your original data is blue. Okay, your EMA6 is red, your EMA12 is green, and your EMA24 is purple. Okay, and then your color blue, red, green, purple. Okay, let's run this. So these are plots of your different exponential moving average. Come on, run. Okay. All right. Okay. Then you can see that the red one is a 6-month, the green one is a 12-month, and then that's the violet one, purple one is the 24-month. You could have added 36 also, etc. Same behavior as your simple moving average. Okay. Then here we're creating this object forecast EMA. Okay. And then we're getting the tail. EMA12, that's our model, and then we get the last value there. Okay, so we're printing the forecasted value for the next period is this one, this object. So you're interested in getting what will be our forecast for the next period. Okay, let me check if this syntax will work. I haven't checked this. No? So forecast EMA is the tail. So should it be 12? Let's see. Control Enter. And then, all right. So it gives us the forecasted value for the next 12 periods. Okay. So using the EMA, you can plot. Okay. For example, we already computed EMA 12. Then we already computed the forecasted value. Okay. Then what's happening here is that we are extending the time of air passengers. Okay, so that there will be the same time. So this will now, I'll just plot this class. And you can see here that this one is actually your, no? Okay. Okay, sorry about this. I will have to check this class. I'm sorry. It should show the forecast value. However, in our plot here, we have the original. The EMA 12 period did not show. I'll have to check this class. And then the forecast did not show. Okay. But anyway, I will have to check our code for that. Okay, same thing class with SMA 12. EMA also is used for technical trading. So usually it's a 12-day and the 26-day. So same thing, class, same rule. We also plotted this before. Okay, you have we're using Tesla here, and then EMA 12 and EMA 26. All right. So here you go. Okay, so there are points here. Your your 12 is sorry, this is not Apple, this is Tesla. Your 12 is your 12-day. Your red is your 12-day, and your green is your 26-day. So where the EMA 12 crosses over your 26, okay, what happens? It's a signal of class. What's the signal? If your EMA 12, okay, if it crosses over, so goes above your EMA 26, what does that mean? The general rule is that when you have a short term EMA or SMA, and it crosses over the longer term EMA or SMA, then that indicates that's a bullish indicator, which means buy. Okay, short term going above the long term, that's a buy signal. Short term going below the long term, that's a sell signal. Okay, so let's now go class 2. I want us to, hopefully we're able to discuss this, exponential smoothing. Okay, so this is relatively more powerful class, more powerful than SMA or EMA. Okay, because the technique here is that what is assigned, unlike EMA, which assigns arbitrarily numbers or weights to more weight to the most current value. Here, what we do is exponential decrease. Okay, that's why it's called exponential smoothing. EMA and SMA are also smoothing techniques, but SMA is just equal yung factors. EMA is varied, however, it's randomly assigned. For exponential smoothing, we assign exponentially decreasing. Okay, so this is ideal for forecasting when the time series has no strong trend or seasonal pattern. Okay, there are of course weaknesses here. So there are several types of exponential smoothing. The first one is SES, simple. Then we'll go to Holtz, and then we go to Holtz and Winters. Here, class. We have simple exponential smoothing. We have Holtz, and then Holtz and Winters. Holt-Winters seasonal model. Here it's Holtz linear trend. Here it's Holt-Winters seasonal. So this takes into account not only trend and seasonality. This can take into account the trend. This, okay, this is best for if there's no trend or seasonality. Okay, so those are the basic ones. Okay, so what's this? This is just okay, this is just the formula class. So your predicted value of y is equal to a certain function, a certain smoothing constant. Okay, so this is multiplied or regressed on past values of your y, and then 1 minus alpha past predicted values. Okay, so you can see that y sub t, the forecasted value, is based on the past original value and the past forecasted value. So that's what makes this SES, okay? This simple exponential method more powerful than your SMA and EMA, okay? So what's the key difference between simple moving average and ES methods? SMA uses a fixed window of past data. exponential smoothing gives greater weight to more recent observations. Okay, and in this regard, it's quite similar to your exponential moving average. All right, so let's run this. The function is just SES class. So simple exponential smoothing. Okay, so we're creating this SES model. We first create a forecast of 12 observations. Okay, and then we create the fitted values here, the forecasted values, fitted SES model. Okay, and then we convert our fitted. Okay, we create this object, fitted time series, where we convert our fitted values here into time series. Okay, so the start date will be the start of AP. The frequency will be the frequency of AP. And then let's plot. Let's plot the data. Okay, the original data, okay, will be black. This is your AP. And then your forecasted value, your fitted time series will be blue. Okay, and then we give a titles here. Okay, so let's run this class. Let's run this. Okay. All right. Now take a look at this class. Okay. So what do you observe about this one's simple exponential smoothing? The black one is your original data. Diba? The black one is your original data. The blue one is your forecasted data. And you notice that your blue one follows your original one, only that there seems to be a lag. So it's just mimicking your observation, your data. Okay? There seems to be a lag. Okay, you can see now there, class, that your blue one is about 12 steps behind your black one because your H is equal to 12 here. Okay, and I have here some explanations, class. SES behaves like the original time series with just a lag in the predictions. Okay, SES, this is your simple exponential smoothing. It's designed also to smooth out short-term fluctuations. Okay, so that your fitted values closely follow the original data, but with less noise. Okay, so you have here your smoothing effect and your lag. Okay, now I explained to you why your SES looks like the original data. And for SES, that is expected because your SES, it's designed to mimic your original data, especially if there's no strong trend or seasonality. Okay. However, there's a weakness of SES when you're modeling a time series with very strong seasonality and strong trend. Okay. Then what will happen is that SES will tend to smooth out your original data. Okay. Now, in our case, the airline passengers, yes, although it has a trend and seasonality, okay. However, I think because of there's fewer observations, only 144. Maybe if this was extended for a long period, then it would show the weakness of SES. Okay. So in order to address that weakness, I I regret having used air passengers. I should have used a longer time frame. Okay. All right. So here, what we now, what we, what do we now have here? So, okay. So this is just the plot of the original series and the forecast. You can see here that you have the original series and then the forecast of 12 periods. Come on, let's run. Okay, there, class. This is your original data, and then you have your 12. H is equal to 12. All right. For this one class, I'll have to, I think I made some mistake here. So I'll not run this first now. I was trying to test and check what was wrong with my code here. Because I'm comparing. Okay, let me just run this. If you notice what's alpha, if you recall class, what's the formula for exponential smoothing? Okay, let me go back here to our formula. It's alpha times your past value. Okay, where's the formula, please? Formula. Okay, here. Oops, that's EMA. Where's my UTS? It's almost time. Oh no. Here, class. Alpha times the previous actual value, and then 1 minus alpha. So if this is 20%, so the weight that you're going to put to the past predicted value is 80%. Okay? So the higher your alpha is, the more weight you're giving to the previous value, previous actual value. So here you have 0.2, 0.5, and 0.8. Okay? So if you run this, sorry for that. All right, it's almost time, class. May I just, okay. Then here is where was having a problem. The autoplot. Okay. All right. So I have a mistake here, class. I will have to backtrace this. Ano yung what was my mistake here? But this run, class, this run. So I wanted to compare the difference between your model if your alpha is 0.2, 0.5, 0.8. Remember, alpha is multiplied to your past value, and then 1 minus alpha is multiplied to your past predicted value. Okay, so it's different from your EMA and SMA because your EMA and SMA only uses your past value. Here, you make use of your past values and your predicted values also. So that's one difference between your exponential smoothing and your EMA and SMA. All right, so to improve, because the SES has a weakness of not being able to address the trend, the Holt's method is able to address the trend. So you make use of Holt here. Okay, so let's just quickly run this and plot, class. Plot. Okay, kindly run. I hope you give me 2 minutes so that we just run the Holt's. Okay, so this is the Holt's method. It's an improvement of SES. Okay, if you take a look at the predicted value, so the red one here is the predicted. It's quite similar to the SES. Okay, it's quite similar because as I said, the length of the period and our data is quite small, 144. Okay, but if we had chosen a longer data, then you would have seen the power of Holt. Okay, and lastly, okay, I have some explanation here why they look similar, SES and Holt. And lastly, plus this one, Holt winter. Okay, this takes into account seasonality and trend. So let's run this. Come on. Of course, class, if you need to go, please. Anyway, this is recorded. All right. And there's the plot here. Okay. Here. You can now see that the Holt-Winter method is a bit more accurate than your SES or your Holt method. Okay. Although in the first few observations, it might not be as accurate as your Holt. But overall, class, the Holt-Winter method is a lot better. So here, let's now compute for the Ramsey of SES, Holt, and Holt-Winter. I just wanted to show this to you, which is more powerful. Okay, so here we're creating the model I recreated the model for SES, for Holt and Holt-Winters. Okay, and then here I'm computing for the Ramsey. Okay, mean of the actual minus the fitted value squared, and then get the average and then get the square root. Okay, so we compute for the Ramsey for SES, Holt, and HW, and then we print. Okay, the Ramsey for SES model is this one, okay, etc. So if we run this, it will tell you which has the lesser error. Okay, which has the lesser error in modeling our AP. Okay, come on, please, there. Okay, there you go, class. You can see the Ramsey for SES is 33.59. For Holt, it's not much difference from SES, but take a look at this. Holt's Winters, 17, almost half less than either SES or Holt. Okay, so this tells us that indeed the Holt Winter is very appropriate. It's the far better model, especially if your data has trend and seasonality. Okay, so I leave you, class, to look at this also, Tesla. Okay, so this one also, please just run this, and it's quite similar to what we did above. This is applied to finance. Next meeting, we're going to do regression. Okay, we're going to use another method. So far we have a simple moving average, exponential moving average, simple exponential smoothing. We have Holt linear model. We have Holt Winter. Okay, these are examples of your exponential smoothing. Next meeting will be regression and ARIMA, and then we also spill over to another very important model. One of the more modern models is your Kalman filter. Okay, and then lastly will be Garch. All right, so thank you so much, class. Let me stop recording now. I hope you learned something, and have a good day ahead.